watched her first lecture online. It was alright. Next thing I was like, she was like, the dog is very high frequency. She goes, no way. Like, spent 5 minutes, like, mine was just following.
She's pretty good actually. She knows that.
Yeah. So I'm going to take a picture. I want to say.
Exactly. I have no idea.
All right, let's get started. Good morning, everyone, and welcome to E141. So before we start with today's lecture, first a couple of administrative announcements. The course webpage is fully linked to all the links that you were looking at the previous week. So you have also a webpage available from the instructional domain. Next week, we will start with labs. And I'm looking into adding another lab on Friday to be able to accommodate everyone. And I will make announcement about that next Thursday when it's finalized. But it will be probably sometime Friday afternoon, 3 to 6 or so. And we will keep the other 3 labs that we had scheduled originally. Okay, and yes.
You say originally, you mean Tuesday, Thursday?
Monday, Tuesday, and Thursday.
Oh, okay. So there's no more Wednesday lab.
No more Wednesday lab. Wednesday is completely booked by E105.
Okay. Is it possible you had a lab on Friday? Like Southie or E, they did send me, they request another lab like on Friday. So can we do the lab on Friday?
There will be a lab session on Friday.
Oh, really?
Yeah.
Oh,
Yeah. Okay. And to be able to do the labs, you will have to have ECS instructional account, which I'm sure you all have already opened so far because you need it for homework 1. And this is a useful link that you can look at to get familiar with the environment that you will find. Yes.
Last night I was trying to use my each instructional account to do the homework, but I wasn't able to copy the 141 files. It said it was restricted. Yeah, do we have a 141 account specifically, or are we just supposed to use our EX accounts?
The question is, are you supposed to use EX account or 141 accounts? And it is recommended that you use your named EX accounts. In special cases, for those who don't have named EX accounts, we can open up 141 accounts. I will thank you for the note. I will look into that to make sure that you have the full permissions, full access permissions, so you can copy over the files. And I will do that right away. Thank you. Yes.
I didn't have a problem with it. I just wanted to point out if he added those lines, there's 2 lines in some text file that you said to add to our .cshrc file or something like that. Maybe if you don't do that, it will restrict you. I don't know.
That is probably not going to restrict you for the access-wise. You will have to have your CSHRC set up to be able to run the software Spice and Cadence, but access-wise, it shouldn't matter. I'll double check into that, and I'll have a posting on the website later today. Okay. So homework 1 is due next Thursday, this Thursday actually. So you can either bring it to class and drop it off before class, or you can bring it to 275 Corey. There is a E141 drop-off box in that room. So that's, you know where that room is. When you enter Corey on the 2nd floor from the first side, you make a left, and on your right-hand side, there is a room with drop-off boxes. And we will also post homework number 2 on Thursday at 5 p.m. So we'll start on a weekly base, weekly cycle for homeworks. TA office hours have been determined. Their office is in 197 Corey. So Lynn will have office hours today from 1:30 till 2:30 p.m. If you have any questions about your homework, she will be able to help you out. And Kelu will have his office hours on Wednesdays, 2 to 3 p.m. Is Kay around? No. He had some scheduling conflict for this week, and I need to check with him if he will be still be able to have his office hours tomorrow, or he will schedule it at some alternative time this week. Also, we have activated the class news group, and I think about 20 people signed up so far. So please use the news group if you have any questions and want to discuss topics covered in the class. You are welcome to do so. And we will be checking the news group pretty often on a daily basis. And we have also enabled this email alias. If you want to email myself and the TAs, you can simply send us email to e141@core.ecs, and we will all receive your question. Okay. So last time we introduced a couple important design metrics that we'll be using this semester, and we'll quickly review some of that material today, and then talk about CMOS manufacturing process and design rules. What do you need to do as a designer to fabricate your chip? So last time we talked about 4 important design metrics: cost, reliability, speed, and power. We are going to finish that up today. So we said that the total cost of an integrated circuit can be broken down into 2 components: variable cost per IC and fixed cost, or non-recurring engineering costs. And from this simple expression, we see that the impact of this fixed cost term can be significantly reduced in a high volume products. And we further analyzed this variable cost per integrated circuit that was attributed to cost of manufacturing, testing, and packaging your design, and it was also inversely proportional to the final test yield. So in addition to that test yield, we also introduced the quantity die yield. And that has to do with the die cost, where cost of a die is directly proportional to the cost of a wafer that you use to fabricate your design. The wafer has a number of identical dies distributed all over the wafer, and that was inversely proportional to the number of dies per wafer and the die yield. And the die yield had to do with mechanical defects introduced in the process of manufacturing your design, and it can be calculated using this exponential formula, where this exponent was related to complexity of manufacturing process. And in today's processes, this alpha term was typically around 3. So having that in mind, in previous formula, we concluded that the cost of a die is a function of the 4th power of the die area. So it was very expensive in terms of having defects. Then we went on to define DC voltage transfer characteristic for a gate, because this was very important to understand reliability and noise immunity of your gates. So for that purpose, we drew voltage transfer characteristic that was characterized on this graph, and what this tells us is basically nominal voltage levels. We introduced nominal voltage level for logic 0, VOL, and nominal voltage level for logic 1 at the output, VOH. And the way we define these terms is that when you apply VOL at the input of a gate, you get VOH. When you apply nominal logic 1, you get nominal logic 0. And also another important parameter that we introduced here was the switching threshold of your gate, which was defined as the intersection of a 45-degree line with voltage transfer characteristic F. And this was V out is equal to V in, and intersection is this switching threshold of a gate. So this was idealistic case. And in most cases in real life, you don't have ideal nominal voltage levels at inputs and outputs of your gate. And there is deviation from this nominal level that we attributed to noise. And there were various noise sources that we classified as internal noise, which is most of the noise that you find in your integrated circuits, and also externally generated noise. So noise sources can be power supply noise, it can be crosstalk in the form of capacitive coupling or inductive coupling, it can be intersymbol interference, it can be timing noise due to clock skew and clock jitter, and so on. And we will analyze these noise sources later on in the semester. But to be able to measure the quality of a gate, then we introduced a couple properties for gates that have good noise properties. Okay, the question? Okay, sorry. We introduced the regions for logic 0 and logic 1, and in between we have this undefined region. So we introduced this VIL and VIH voltage levels at the points where the slope of this voltage transfer characteristic was 1, -1 in this case for the inverting gate. And the reason for that, as we saw, was that the gates with good noise properties have regenerative property, which means that if you apply any voltage signal in this bin between VIL and VIH in a chain of gates, you will be able to recover close to your nominal values. And in order to be able to do so, you have to have a gain larger than 1 in this undefined transition region. So using these values of VIH and VOL, VIH, VIL, VOL, and VOH, we defined noise margins that quantify the ability of your gate to work in a noisy environment. And we defined noise margins for logic 0 and logic 1. So noise margin low was defined as the maximum input voltage at the gate that will be read as input logic 0 and the nominal output logic 0, VOL. So, and in a similar way, we defined the noise margin high, which was the difference between the nominal logic 1 and the minimum voltage level that is still treated as logic 1. Okay. And then we introduced the ideal gate that has all the good properties from the noise margin standpoint and also drag capability. So for the ideal gate would have logic level 1 at VDD, logic 0 at 0. It will have VDD over 2 noise margins, so it would be able to tolerate quite a bit of noise. It should have 0 output resistance to be able to drive infinite fan out, and it should have infinite input impedance, so it presents no load to the previous gate. And this is idealistic concept, but it serves well to be able to investigate the quality of gates, how much they deviate from this ideally desirable case. So then we start talking about the speed, which we'll finish today. And we said that the performance of a gate can be quantified in terms of this propagation delay, and we defined propagation delay between 50% transition points on input and output voltage waveforms, and this 50% is motivated by that switching threshold that we saw in the few slides back. And we defined 2 delay quantities, TPHL, which is a propagation delay when output signal undergoes falling transition, and we also define TPLH, which is a propagation delay experienced when by an input signal when output undergoes a rising transition. And these 2 delays, TPHL and TPLH, which we defined relative to the output of a gate, have real physical meaning because you can really observe and measure them on your waveforms. And we also defined the average of the 2, which sort of doesn't have much of a physical meaning, but it kind of tells you to first order about the relative speed of your gate if you want to compare different gates. And there is a number of parameters that affect your delay. So these are just idealistic assumptions, and you really need to understand the environment in which you're evaluating your gate. So how many gates are around? How many gates do you have at the output of your gates that you need to drive? How much parasitic capacitance that you need to drive? What is driving your gate on the input side? And that defines the shape of your voltage waveforms. And for that reason, we define the rise and fall times, because delay really depends on the slopes of these waveforms. And we define rising and falling times, again, relative to the output side of a gate. So you have the fall time that takes this waveform to go between 90 and 10% transition points relative to the full voltage swing, and also rise time, it's 10 to 90% of between 10 to 90% of transition points. And later in the class, we will introduce correction for this delay formula. You will have basically propagation delay of the gate itself plus some linear term that is proportional to the slope of your input signal. And this was the delay definition that was attribute of a certain gate, but it's also interesting to see how do different gates compare across technologies. And for that reason, we introduced this ring oscillator metric for delay calculation, where we actually are able to evaluate the relative capability of a technology to deliver a certain amount of performance. So that was kind of a first hand approximation and understanding of how fast your technology can go. And that can be evaluated in this ring oscillator configuration, when you have even number of stages, so that you can have oscillations in this structure. And you typically have to have at least 5 stages for a ring oscillator to work correctly with the right waveform shapes. But normally you have maybe around like 20 or so, but it has to be even number. And so the total period for a signal to go between 2 rising or 2 falling transitions is given by this expression here. Period of oscillation is equal to 2 times the propagation delay, which is the average of low high and high low that we introduced from in the previous slide. And if you actually do a little thought experiment, you can put this ring oscillator together, and then you can see for the half period how many low to highs and high to lows you have. For the other half, how many you have. And you will exactly end up with this number, that you have 2 times the average propagation delay between the 2 times the number of stages. And this was a useful metric to evaluate the capability of a technology, but we had too many simplifications in this case. Number one is we have very simple gate, just a simple inverting function, and number 2, we assume fan out of 1, unity fan out across the structure, which doesn't really give us a realistic estimate of the speed, the clock speed and performance at the higher layers in design abstraction. So normally the clock speed is about 20 times slower than this propagation delay of a single inverter in a ring oscillator configuration. Question? Yes.
You mentioned the minimum number of gates in this ring oscillator is 5. Why not 3? Why can't 3 work?
That is just an empirical number. So the question is, why is the minimum number of gates equal to 5? And if you can switch to the overhead camera, please. So we have this relationship that the period of oscillation has to be significantly larger than this rising and falling delays. And if you have very few number of stages, then you more likely have like a sinusoidal wave, and it's not really quite going to undergo the full rising transition by the time it's getting triggered with another transition and wants to go low. So you may have a reduced swing and also not so good signal slopes. Ideally, you would like to have really good quadratic waveform for which you have to have a large number of stages, so that you make sure that if you go around the oscillator, next time you come back to this point, that all the transitions related to this gate have been settled It's not that this gate was somewhere in the middle of a transition and you trip it with another switching event. Okay, so go back to slides, please. And for the purpose of comparing different designs, we also introduced another technology-independent metric, which was a fan-out 4 inverter, which has a more realistic parameters. We have fan-out at the output of this gate of about 4, which is about the good fan-out that you find in your design practice. And this actually circuit serves as sort of a benchmark to be able to compare various architectures, so and evaluate how many stages do you have in between pipeline registers, and sort of determine the clock frequency is often quoted in this fan-out 4 numbers. So say, let's say your clock is 10 fan-out 4 inverters or 20 fan-out 4 inverters if you have different architecture for different application and so on. So that's an important circuit to remember. And oftentimes we analyze behavior of digital circuits and gates in particular using this first order RC network. And we can calculate propagation delay using this simplified model. So we have we basically have an input voltage source that performs a step transition at the input, and then we observe the output waveform that has that is approaching the value of this input over here in an exponential fashion. And it's actually pretty easy and intuitive to derive this formula if you go back to the overhead. So when you have, basically you have your source over here, and then you have your RC network, with R being attributed to your equivalent pull-up or pull-down resistance of a gate when it's charging the capacitance to a logic 1 or discharging to logic 0, and you have your load capacitance CL here. So you have V out. So now you can pretty much, knowing that this is exponential law, which actually comes from the fact when you put together Kirchhoff's laws for this circuit, then you will see right voltage and current relationships. You will see that exponential dependence of the output waveform. So if you have this input waveform going from 0 to V, then you have simply that your output has to settle at value in infinity when you let infinite amount of time after this step. And you also have this exponential term, e to the minus t over tau, where tau is this time constant defined by our CL, C load. So what you have to have in between, basically, when t is equal to infinity, then you have this value after infinite amount of time has passed. And when t is equal to 0, this term is 1, so you have to subtract this off, and you have basically V0 minus V infinite. And then your V infinite is equal to, because there is no DC current through a capacitor, so you have this value here to be equal to V, and V0 was equal to 0, because the capacitor was originally discharged. And you can come up with simply with the formula that it's V1 minus e to the minus t over tau. But this is pretty much the concept that you can use all the time to quickly come up with the formula that you can calculate your output waveform as a function of time. So this is V out of t. And then the propagation delay, the way we defined it, was when the output waveform reaches the 50% of the full swing. And when you put that together in this, put that in this equation, that you have basically that you have V out is equal to V over 2, that is equal to V times 1 minus e to the minus Tp over tau, then you have that your Tp is equal tau ln2. And that's a very common formula that you'll be seeing over and over again this semester. Okay, let's go back to slides, please. And this ln2 is 0.69 RC. You'll be using this number quite often in calculation of the propagation delay. Okay, so now we are going to introduce the final and the most important metric in today's designs, which is power consumption. So power actually tells you two things. It tells you about the amount of energy that you store on the load capacitances and also the amount of power that gets dissipated as a heat. So it's those two things. And there is a number of parameters that you need to worry about when you design your circuit, but you always start from this very basic definition of instantaneous power. So that is, at any given point in time, your power is expressed as the product of the voltage at that time and the current. And this is applicable for any node in your circuit, but we are mostly interested and concerned with the global power consumption out of our supply voltage. And for that reason, we normally look into VDD, which is constant over time, times the supply current that changes depending on the switching events and so on. The peak power consumption is basically average power over some period of time where you take the maximum of this current over that same period of time and you define this peak power. The reason why peak power is important is that you have to design your power distribution network for the worst case to be able to support all these transients when you have more current than average for your circuit to work. And the average power is finally the power metric that is most commonly used in design practice. That is the power that causes you all this heat dissipation and power density problems and all those headaches. So that's basically the average over a period of time of your instantaneous power taken out of supply voltage. Okay. So the speed of your circuit and power consumption are really related because the propagation delay is actually the speed at which you can charge certain amount of energy into your gate capacitance. And the faster you go, the more power you dissipate. The product of the two, power delay product, is normally constant for a given gate and a given topology. So that is the energy per operation. So you have energy defined as the product of your average power consumption and propagation delay. But the energy is constant, and that's good. So you can pretty much evaluate how much energy you need to spend to perform a certain operation and evaluate the cost of performing that operation. But you really want to sort of have and understand. You need to understand really two things. One is how much it takes to perform an operation, and also how fast you can do it, right? And for that purpose, people normally introduce this synthetic metric that has no physical meaning whatsoever, but sort of nicely quantifies the gates, the compromise between power and performance. So this is energy delay product, which is the quality metric of a gate, expressed as a product of energy and propagation delay. And going back to the overhead again, please. So what you really have in each digital circuit on energy delay, propagation delay axis, when you tune various parameters, for example, one being a supply voltage, which you are probably the most familiar with, you end up with some fundamental relationship like that. You have a trade-off. The faster you want to go, the more energy you need to spend, and so on. And when you actually plot your energy delay product on the same graph, what you get is something like this. So this is your EDP here. And minimum energy delay product occurs at this point where you have basically slope of -1, which is basically the best energy performance trade-off. You can invest 1% of what this slope of -1 means. You can invest 1% of energy to go 1% faster in your performance. And if you go either toward extremely high performance or extremely low energy, then you are paying too large of a price. So you have too large of a price in energy to going going fast, which is quantified by this energy delay product. But in essence, you have this energy performance trade-off that you need to understand, and everything comes from there. Okay. So going back to slides now. So now we can again analyze the power consumption of energy rather delivered from this voltage source. So when you have a step input at your input, then a certain amount of energy gets transferred over to a network that's consisted of this R resistor and a load capacitance. So now it will be interesting to calculate the total energy that this source provides, delivers to this network. And it's simply, you can integrate power over a period of time, and this T is long enough such that all transients have been settled. And that is pretty much, if you go full swing from 0 to VDD, then you have, because you have a step input, you have VDD, and you need to integrate this current that goes through this RC network. That you know that's equal to C dV over dt, so you end up with VDD C dV over that period of time. That corresponds to a voltage transition from 0 to VDD. So that was your V infinity, or T in this case, where T is rather large. And then you have C times VDD squared. So this is very important relationship that you will find, that the amount of energy that is injected from this source into your network is CV squared. So it's quadratic function of voltage. And obviously, if you are power conscious designer, you would like to reduce your supply voltage as much as you can, because that's the most dominant variable in your energy optimization. So now let's see how much energy is stored on this capacitance, on this gate capacitance at the output, because that is actually the useful energy that is related to the information in digital format 1 or 0 at the output of your gate, because you would want to spend a certain amount of energy to be able to say, okay, I have a high voltage here, that's my logic 1. So for that purpose, you simply integrate, to calculate the energy, you integrate the power of that capacitor over time. And the power is, as we defined it, is the product of the output voltage and the current that goes through that element, this capacitor. And then you have this current relationship that you have C dV over dt, and this becomes dt cancels out, so you have C times V out times dV out, where this voltage at the output goes from 0 to VDD. So when you integrate, you get half of this total energy. So what happened to the other half? Right. So it basically got dissipated as a heat on this resistor. So the energy that is provided by the source tells you about the amount of energy you need to perform a useful transition and the amount of heat that you have dissipated in your circuit. So you always have that the energy to perform some useful charge or discharge operation is equal to half of the total energy, where the other half is dissipated as heat. Okay, so this completes the design metrics that you will find over and over again in this course. And now we are going to go really all the way down to understand MOS transistor and a little bit of manufacturing process before we go into and define interesting parameters for gates, like current voltage relationships of a transistor and propagation delay and so on. So this is really not a topic of this class, and so we'd rather go quick through this material, and you can read it in the book. But it's very interesting to see really where all these things are coming from, how your device is manufactured. And you may think of a transistor as a really like some simple structure, because all these devices are kind of tiny and packed close to each other, but it's really a three-dimensional structure. It's really complicated. So shown here is a photo of the MOS transistor, NMOS in this case, where you have all this P-type substrate, and then you have a gate polysilicon gate, and you have diffusion regions where N plus highly doped diffusion regions that define source and drain that are interconnected with the rest of the world with aluminum wires. And you have field oxide, and you have also gate oxide as isolation from other transistors, and you have gate oxide on top of your channel. So this is kind of a complicated picture to look at, and normally what you do is actually you take the cross-section view to understand what's going on. And here's a cross-section view of a CMOS process. As I said, that today's processes are CMOS, which means that in a single manufacturing run, you are able to manufacture both your NMOS and PMOS transistors. And this is actually a CMOS process more of the 80s. It's a rather old process that you have shown here. So you have a lightly doped P substrate, and then you grow your NMOS transistor in your P substrate, and you have a polysilicon gate on top, source and drain contacts, and the gate oxide underneath. In order to make a PMOS, you have to have an extra region here called N-well, because your transistor is always the opposite polarity from its substrate. So you have P plus regions that define source and drain, and you have also this huge oxide, thick oxide in between the transistors to make sure that you really isolate source and drains of the two devices so you don't introduce parasitic devices. And you have aluminum wires that define interconnects. So here's a look at the modern CMOS process, where several things happen. So first you have this highly doped P plus material over which you have lightly doped epitaxial layer, P-epi, and then a couple differences compared to the previous process. In previous process, we had all this huge thick oxide isolation between the devices. And now we can, manufacturing process improved dramatically, so we can do dry etching, plasma etching. So you can really drill through the material in a very precise way, and you can form these trenches that you later deposit silicon dioxide in between, and you can have much closer, much tighter spacing between the two transistors, which also increases your density. And also, previous process was a single well. Today, almost all processes are dual well processes, where you have basically, to create your PMOS, you have this N well here, and then you have ion implantation of your source and drain regions, and you create a P well for the NMOS transistor. And also, aluminum wires were mostly replaced by copper interconnect. And also on the gate of a transistor, you had a polysilicon. Now you have more complicated structures. You have the poly had a problem that it has rather high resistivity. And in order to improve the performance of your circuit, you really have to worry about that effect, and introduced coating of this silicide layer on top of your polysilicon to make it more conductive. Now the question is, why don't you make your entire gate with this silicide layer? The problem is that it doesn't bond well with this channel oxide here, gate oxide. And so you have to kind of make a sandwich. You have polysilicon, and then you have this silicide layer that improves the conductivity. And really, starting from here, you can expand all the way up, stack up all the way up vertically up to 7 metal layers today, 90 nanometer CMOS, where your transistors look really tiny and a huge skyscraper on top of it. It's really like a foundation. It's quite amazing how these things work. So why this is important for you is because you will be eventually making a set of masks for laying out this transistor. And if you look at the cross-sectional view, that's what we had before. So basically, a transistor is composed of source and drain regions, well region, and you have a poly. Then you have aluminum metal connect, and you have vias, which is basically a hole that is filled with metal that connects your source regions with the metal. So this is the layout view. That's what you're going to do in your software labs. in 353 to get familiar with these tools. And you will be actually looking at your layout from top and define all these layers. So there is basically a sequence of these layers. You can define, you can put either first poly and then you can put active on top of it, or you can put active poly. It doesn't matter in which sequence you do it. It's basically just, it's important that you understand how this works and to be able to define a proper set of these rectangular objects, because your layout is a set of rectangles that are attached to certain manufacturing layers. And that's what you're going to do in your labs when you create layout. So in this case, you have basically, you have a P well. So this is an NMOS. And then you have diffusion region here for your source and drain. You put poly on top that defines your gate. And then you connect source and drain. So this is an example circuit that you will do in, I think, software lab, either 2 or 3, I don't remember. But you will have to basically create a chain of inverters. And the point here is that you want to eventually, when you have sort of repetitive patterns, you would want to have layout for one and then just have array of those, because that will save you a lot of time. So this is a view of a CMOS inverter in layout. So we have this N well where you put your PMOS. So this is your source. Then you have a drain. Then you have NMOS here with source here connected to ground and drain. Then you have a common gate that defines your input signal. And then the finally drain, so these two transistors are connected at the output, which goes in metal 1. And then you have a bunch of these contacts for your well and also for the output contacts with active. So these are the kind of things that you will be doing in your labs. So when you have two inverters, you just put them next to each other. Layouts, put them next to each other, and then you connect output of the first gate to the input of the second, the consecutive gate in metal 1, and you are done. So these are some simple exercises to get yourself familiar. So now we will watch an instructional video that illustrates manufacturing process steps, and you can also read that from the book. But this is really interesting to see in motion and how all these things are done, from starting from the crystal growth all the way to manufacturing, going through these various steps, and then slicing the dice, packaging, and all that. So we'll take just a moment and we'll go to the video. So audio will be coming shortly, I think.
You know, we might not have the audio. We had to switch decks here before class, so I don't know if we'll have the audio for you. Sorry.
No audio.
Maybe you can narrate.
Excuse me? Yeah, I'm trying to. Would it be possible to switch decks back now so that we have audios, because we'll want.
Sorry, I'd have to take this rack out, and it's just too involved. I'm sorry, I can't do it right now.
Okay. So I guess maybe we can do this next time, perhaps. Is that?
If you want to go back to your slides, I can try reconnecting the cables, but it's
Okay.
a bit of a process.
Thanks. Okay. Was a nice try. So this is basically all the steps that you will be watching on that video sooner or later. And I will skip through these slides that describe this whole process that you will see on tape. This is all in the book. So okay, now it's really interesting to see here, like after you go all this steps, then you have really this number of metalization layers on top of each other, and then you have these vias in between, which is a hole that connects filled with metal that connects to adjacent metal layers. And you can, as you can see, this can look pretty complicated. As I said, initially people mostly used aluminum wires, but copper offered much better conductivity. There were some issues to make it economically feasible, and finally this shows IBM's process that kind of got a handle on this problem. This was in '98, and now more and more processes use copper metalization, where you can basically just fill your metal with this into these trenches, and then you do mechanical polishing on top to even the structure, and then you can continue building up. But this is really, like, although it seems really complicated, it's a bunch of for each of the layers you have basically a bunch of predetermined sequence of steps that you just go around and build the structures. So I'm now going to skip over to design rules and layout, and we will get back to manufacturing later, because this is really what you need to know for your labs and for your class. So the design rules is actually a contract between a process engineer and design engineer. So you need to have some interface, common interface that you both understand to be able to transfer your designs over into layout. And normally these design rules have been traditionally expressed in terms of these scalable rules and lambda rules. You probably heard of those, where when you can actually scale the minimum feature size, minimum width and length across technologies by just scaling this lambda parameter in a linear fashion. But the problem with these rules is that not really all the parameters follow linear scaling relationship. And also, when you want to compare different technologies, you need to take the worst case over the entire set. So you basically end up with the conservative rules that don't really give you good density and so on. So more recently, and these lambda rules are still kind of in use, but most companies now use these absolute micron rules. So when you have a technology, you have all your rules expressed in absolute metric units. And there is a couple things you need to know. There is obviously your palette, your set of layers that you're going to use. So you're like an artist. You have your palette, and you can choose different colors, put polygons together, and make your artwork. And besides the set of layers, you need to know certain rules that these layers have to satisfy. So we classify them as intra-layer rules, which basically define the widths and spacings of objects on the same layer. And those are related to granularity of your patterning process that's related to these optical masks and devices that are used to transfer your design over onto semiconductor material. That's minimum width determines what is achievable in a certain
Integrated circuits have drastically changed the electron. Integrated circuits have drastically changed the electronics industry and have become an integral part of our society.
Is it okay if I use your phone?
Okay. They are used in sophisticated electronics and computers, which are part of our everyday lives.
Hi, I'm not here now, but leave me a message and I'll get back in touch.
Hello, Carla. My name is my name. I'm using head movements to move the mouse cursor around and speech to do all kinds of words and commands.
These computers are used extensively in research and development to improve the quality of our
Voice
lives.
console. Wake up. Press button. Period. Go to sleep.
The modern electronic era bloomed when thousands of transistors and other electrical components were integrated on a small slice of crystalline material. Today's chips contain millions of transistors and are the heart of the microelectronics, communications, and computer industries. Inside a computer, there are rows of these tiny devices, each one capable of storing information or executing hundreds of millions of operations a second. Integrated circuits have evolved from bulky vacuum tubes and transistors and are fabricated in technological centers like Silicon Valley. It all begins with the growth of pure silicon crystals. Silicon is the common element found in sand. It is 28% of the Earth's crust and second only to oxygen in abundance. The silicon from the sand is refined and purified as polysilicon chunks. The purified silicon is then heated to a molten state. A small solid piece of single crystal called a seed is gently lowered into a rotating vat of molten silicon. Using the cubic atomic structure of the seed as a pattern, a new crystal will form as the symmetrical extension of the original seed. The hot liquid silicon in contact with the seed begins to cool and solidify as it is gently pulled from the molten region. The cubic atomic structure of silicon consists of atoms with 4 electrons in their outermost shell. In a perfect crystal and at low temperatures, each silicon atom bonds with its 4 neighbors. There are no free electrons to conduct current. At room temperature, however, the silicon crystal has enough thermal energy to free a small number of electrons. These free electrons conduct current, as do the holes where the electrons have been. This conductivity can be increased by adding impurities called dopants. Dopants are elements which are similar to silicon in atomic structure. There are 2 types of dopants. N-type dopants, like arsenic or phosphorus, have 1 more valence electron than silicon. P-type dopants, like boron, have 1 less. When some silicon atoms are replaced by arsenic or phosphorus, the crystal is called N-type, due to the extra electrons or negatively charged free carriers. If boron is used, the missing electron behaves very much like a positive carrier. The crystal is called P-type. These free electrons and holes move through the crystal, conducting electrical current in response to applied electrical fields. After 48 hours of growth, a single crystal results from the liquid melt. The ability of silicon to be either a poor or a good conductor by fine control of dopant concentration makes silicon a member of a class of materials known as semiconductors. The shiny rippled surface of the crystal is ground to form smooth, uniform ingots. A curved diamond-edged blade saws the ingot into wafers that are as thin as possible without being too fragile and difficult to handle. The wafers are scrubbed and the edges are rounded off and beveled to reduce chipping. The wafers are then ground smooth on both sides to obtain a consistent flatness and thickness from wafer to wafer. They are rinsed and etched in chemicals to remove surface contamination. The final polish is done on only one side of the wafer. The characteristic mirror-like luster is free from scratches and contamination. The wafers are measured for resistivity, which is a function of dopant concentration. They are inspected, packaged, and sent to fabrication areas, where they will be made into integrated circuits. Meanwhile, teams of engineers work together to design circuits that will be fabricated on the wafer's surface. In this facility, over 100 specialists are often required to design the next generation of a microprocessor.
You can actually increase the number.
The organization of a design team corresponds to the organization of a completed chip.
Right now our iCache is like 32K.
So let's at least offer them an option which gives them the performance.
Computer architects, working at the highest level of abstraction, define the overall function of the chip. They establish the microarchitecture, which regulates the timing and sequences of instructions that tell a microprocessor what to do. The design is divided into areas that perform specific functions. Each unit is assigned a logic designer, who works at the logic level to create more detailed specifications and establish hardware needs. Each unit is further subdivided into functional blocks. Each block is assigned to a circuit designer who works at the transistor level.
Alignment shifter, and for this alignment shifter we should be picking.
The design becomes a maze of interconnected microscopic switches, known as transistors. These transistors turn on and off hundreds of millions of times per second, and in the process, either amplify incoming electrical signals or represent this information as a digital 0 or 1. These two states make up the code used in modern electronic communications. They are the logic or language that computers understand and translate into useful operations. To see how transistors work, let's examine a pair of CMOS complementary metal oxide semiconductor transistors. The N-channel transistor has two heavily doped electron-rich N-type regions, separated by an electron-poor P-type substrate. The electron-rich regions, called the source and drain, become the ends of an electronic switch, which is normally off. The gate electrode is close to, but electrically isolated from, the P-type region. The application of a small positive voltage creates a net positive charge on the gate. This charge attracts electrons from the drain and source regions, turning the switch on. When the gate voltage returns to zero, the transistor is again off. In the normally off P-channel transistor, heavily doped P-type regions are separated by a lightly doped N-type substrate. The application of a small negative voltage repels electrons but attracts the positive carriers, turning the switch on. It is possible to fabricate both P and N-channel transistors on the same wafer by doping sections of the wafer. This is known as complementary MOS, because a gate voltage which turns a P-channel transistor on turns an N-channel transistor off. To illustrate this complementary switching, a top view shows current flowing through the P-channel transistor in the upper left. A voltage signal entering the gate electrode turns on the complementary N-channel transistor, allowing charges to drain through. This opens the lower set of P-channel transistors so the current flows through them. In this way, electrical signals can rapidly propagate through a complex maze of switches. Designing these circuits requires software and hardware tools like computer-aided design and computer-aided engineering. After circuit designers complete each block of circuitry, the computer checks for accuracy based on geometrical and electrical design rules. A mask designer takes the circuit schematic and manually lays out the channels in each layer of the mask and generates a master blueprint. These drawings are usually 400 or 500 times the actual size of the chip and enable engineers to visually check for errors.
Exactly the same clock, so you come in, tap, and then expand.
This information is electronically fed into a computer-controlled electron beam machine. In an ultra-clean environment, a fine electron beam will etch the patterns onto a series of chrome-plated glass plates. After the glass plates are etched, they become the masks that are used to transfer the circuit patterns onto the wafer. Each mask is inspected to ensure the patterns are good. The masks undergo a final wash in acids before they are carefully packaged. The following simplified sequence shows how masks are used to build transistors step by step. The first mask creates a well of doping so that the neighboring N-type and P-type substrates exist on the same wafer. The P and N channel regions are specified and electrically isolated by the growth of silicon dioxide. Next, the gate electrodes, which turn the transistors on and off, are formed. Masks number 4 and 5 define the source and drain regions of the N-channel and P-channel transistors. The next mask defines the contact holes, which will enable the aluminum wiring used to interconnect the individual transistors to contact the source, drain, and gate region of each transistor. Most integrated circuits use from 12 to 25 masks, depending on the complexity of the circuit and the type of process. And now, let's go into a research laboratory and follow a very simplified version of a CMOS fabrication process. From start to finish, a complex process may involve hundreds of individual operations and may take a number of weeks to complete. To have a successful run, control of contamination is extremely important. It takes just a few microscopic dust particles to drastically reduce the yield of effective semiconductor devices. The equipment, gases, and chemicals that come in contact with the silicon wafers must also be of the highest purity and free of contamination. To start CMOS fabrication, P-type wafers with a specific resistance are selected. All types of integrated circuits, including CMOS, are fabricated using 4 basic techniques. Formation of thin layers of silicon dioxide, introduction of dopant atoms, deposition of a variety of insulating and conductive materials, and precision patterning of each of these layers. Before the process begins, the laser-scribed identification number of each wafer is recorded. We start by cleaning the wafers in hot acids. Hydrochloric acid, sulfuric acid, hydrogen peroxide, ammonium hydroxide. That's what it takes to remove all the organic and metal contaminants. This cleaning procedure is repeated throughout the process to make sure the surface of the wafers stay absolutely clean. The wafers are rinsed in deionized water and spun dry in filtered nitrogen gas. In a vertical furnace, high temperatures will be used to grow a layer of silicon dioxide. Silicon dioxide is a glass-like insulator which protects the silicon substrate beneath it from unwanted reactions. Pure oxygen reacts with the silicon surface in a hot furnace to grow a thin layer of silicon dioxide. This process is similar to the way the sun's heat and the air's oxygen turn the shiny new paint job of a car to a dull coat over the years. The silicon dioxide layer will be etched and used as a stencil to dope specific regions of the wafer. But first, the pattern for the stencil is applied to the silicon dioxide through a photographic technique called Photo-Lithography. The first mask pattern will be transferred onto the wafer using photoresist, a material which is sensitive to light. In slow motion, we can see the thick photoresist, which is a resin dissolved in solvents, evenly spread over the surface. The wafers transfer to heating plates and bake at low temperatures to evaporate the solvents, leaving a thin layer of resist. The wafer then enters a computer-controlled machine called a stepper. Inside, the wafer is positioned underneath the selected mask pattern. Ultraviolet light exposes the pattern across the surface of the wafer. In this way, many chips are made on a single wafer. By increasing the diameter of the original crystal, larger wafers are sliced and more chips can be made on each wafer. The wafers are then developed. There are two types of photoresist, negative and positive. A negative resist hardens when exposed to light and remains on the wafer when developed. In this run, a positive resist is used. When exposed to light, the resist changes chemically and is removed when developed. The regions of silicon dioxide, now unprotected by photoresist, are then etched. Although acids can be used for etching, most wet chemicals etch in all directions at equal rates, which can result in undercutting of the photoresist. Undercutting could create an inexact transfer of the mask. When a critical fine etch is needed, the wafers undergo a dry etching process called plasma etching. In the plasma chamber, a chemically reactive gas provides free fluorine atoms, which react with the exposed silicon dioxide to leave sharp vertical walls. High magnification SEM photographs show the precision of these etched regions. The hardened resist is then removed in a dry process, using oxygen plasma, which may include fluorines, followed by hot acid baths. This leaves a stenciled silicon dioxide layer as insulation. Photolithography will be used with each of the subsequent masks in the process. This technique allows us to isolate microscopic regions of the wafer and construct them into components of the electronic circuit. In this way, the transistors and circuits are gradually built, a layer at a time. In the ion implanter, dopant ions will bombard the wafers to create N-type regions. The depth of the ion implantation depends on the amount of energy used. Dopant ions are separated from other elements and accelerated to high velocities in a strong electric field. The ions are then driven into the wafers, implanting the exposed silicon regions. The silicon dioxide layer on the wafer blocks the dopants from unwanted regions. Because these wafers are p-type, phosphorus ions, which are n-type dopants, are implanted. Exposing the wafers to high temperatures diffuses the ions deep into the silicon substrate. This creates a well of n-type substrate where the p-channel transistor will be built. If the wafers were n-type, then boron would have been implanted to create p-wells. A new thinner layer of silicon dioxide is regrown, and its thickness is carefully monitored and measured. In a deposition furnace, a layer of silicon nitride is deposited over the oxide layer. The nitride layer prevents additional growth of the silicon dioxide layer and protects the region where the transistors will be built. Photoresist is again evenly spread on the wafer and baked in preparation for the next mask. Using a computerized machine, each new mask is perfectly aligned to the pattern already on the wafer. The second mask, used to define the actual transistor regions, is also exposed across the surface of the wafer. The wafers are developed to remove the exposed photoresist, then rinsed and baked. The wafers are then plasma etched. The the free fluorine atoms react with the exposed nitride. After the photoresist is removed, the wafers go back into the oxidation furnace. A thick insulating layer of silicon dioxide, known as field oxide, will be grown where the nitride has been etched. To grow these thick layers of oxide, oxygen combined with hydrogen is introduced on the wafers as steam. This insulation reduces the electric fields between the surface and the underlying regions. Through the microscope, the field oxide looks like white boundaries. It will block the current from leaking between devices, allowing thousands of transistors to coexist in a small area. The remaining nitride layer is then removed by a combination of dry and wet etching. The wafers are then implanted with boron ions, which penetrate the silicon substrate only through the thin oxide layer. This provides uniform electrical characteristics in the regions where the transistors will be built. This thin oxide, which may have been damaged by the implantation process, is removed and a new layer of silicon dioxide is grown in the gate area. In the vertical furnace, the gate electrodes will be formed by depositing polysilicon. Polysilicon consists of many small grains of silicon, which will be doped with phosphorus, an N-type dopant, to make them more conductive. With photolithography and the next mask, the polysilicon layer will be etched to create the gate electrodes that turn transistors on or off. To carefully control this etch step, the polysilicon is dry etched. The width of these gates determine the distance that separates the source from the drain of the transistor, and ultimately the speed of the circuit. The remaining photoresist is removed once again. The gates become the first conductive layer connecting to different transistors. Mask number 4 allows the implantation of the N-channel regions with a high concentration of N-type dopants to form the highly conductive source and drain regions of the N-channel transistors. Mask number 5 uncovers regions in the P-channel transistor, which are implanted with a high concentration of boron, a P-type dopant, to create the source and drain regions of the transistor. The photoresist is stripped, and again, the wafers are cleaned. In a furnace, the wafers are annealed, and defects created by ion implantation are repaired. Next, a thick insulating glass layer is deposited. The many different layers previously deposited and patterned are completely covered, leaving an unleveled glass surface with varying depths of fields. To ensure every part of subsequent mask patterns are transferred in sharp focus, the surface must be planarized. A chemical-mechanical method is used to polish down the thick oxide layer on the wafer surface. This creates the flat, level surface required for producing high-resolution patterns. Photolithography and mask number 6 define the openings through which the metal wiring will be able to contact the source, gate, and drain regions of each transistor. By plasma etching the unmasked portions of the silicon dioxide, contact holes are created. Through the microscope, these holes are seen as the small dots. In most chips, these contact holes are so small, they must first be filled with a metal plug to ensure a solid electrical connection. Tungsten metal is deposited over the surface to completely fill these tiny holes.
So we're going to stop the video here, and I think you've got the idea of the way this is going. And next time we will finish with the design rules and then talk about MOS transistor. Thank you. Yeah, I sent you a reply last night. It would be good if you can suggest alternative time because we didn't have discussion this week. 353 Lab is free today if you have time, or you can do it.
I can shift it back by an hour.
Sure.
Okay,
I'll
good, yeah. Make a post somewhere.
Yeah, of course. Okay. Super. So
I work at E140 together.
Is there anything else?
That's pretty much it. I have a CD for you with the homework.
That'd be great.
Yep.
So,
I missed the core video.
Yes.
I downloaded one, but I don't know where I can print out the
Oh, the printout. Do you have access to printers?
I don't have my own.
Do you have? Can you print from instructional classroom 199 query?
Yeah. If that doesn't work, you may try 353 query up on the third floor with the labs. Will be.
Good. 353. Thank you so
Sorry
much.
for the little.
That's fine. I should have.
No, we had a. No, it's all right. We had a little last minute. You know, I got to get behind that rack, and there's 6,000 connections, but I got it. So all's well that ends well.
It works
Sorry
well.
about that. Yeah, no, it does work well.
Yeah, I should have told you on Thursday, but I forgot.
No, that's okay. No.
I think I forgot to turn on the mic, but I think you picked
Yeah,
it
we
up
got
well
you
for
on
this
that.
one.
Yeah.
I'll make sure I do. No problem.
All right. So funny, this is a good quality tape. Usually the tapes we get in here are duplicates of duplicates,
Oh, really?
you know, dubs, and so the
Yeah,
quality.
this one out from the library.
Yeah, so bad that you can barely see them. Hello.
Yes.
I was registered for the Monday lab, but my time will be more.
Okay, so that's pretty well done.
So it is a lab on Friday. So what would be the time? Is it like 3:30? Okay.
That's works. Okay, good.
I noticed you show the slides from your laptop.
Yeah.
And then if you have to write something down with me.
Right here.
So they can
Yeah,
seamlessly switch back and forth.
Yeah, you just tell them switch to the overhead, and then you can see on the program, on this monitor, you see your slides, and over here you see what you're writing on.
Yeah, this is a waste of paper. I print them out.
Yeah, this works well. Sometimes I find it more convenient just to write because slides, you fall asleep or things.
True. I have noticed that too. That if you stop writing, then
They're just like.
take care.
I got it. Sure. Okay. See you on Thursday. So I guess we can fool around with the website a little bit, update your office hours.